Hello, ladies and gents. We're going to take a look at how to use Excel to calculate probabilities for the t-distribution and confidence interval. This is Unit E stuff. So let's take a look at some things here. I want to introduce you to a document. I've actually copied the page over, but the document is called Critical Values and P-Values Using Excel. And you'll find this particular document in a couple of places. You can take a look in the supplementary files folder, and it will be listed there as a Unit E file. It's called Critical Values and P-Values Using Excel. You can also find this at the very end of your book. So take a look at your manual at the very end where they've got all of the tables and the formula sheets and so on, and you will find 2 pages here, which is the critical values and p-values using Excel. And I want you to know these formulas here quite well. It basically comes down to 2 types of formulas. There's inverse functions and there's DIST functions. So I'm actually going to start with the DIST functions. And when we get into Unit H, we're going to use DIST functions to calculate things called p-values. Now, I've briefly mentioned p-values before, but you really want to put that aside until we get to Unit H. But DIST functions are things that you've been using all along, actually, since Assignment 2 and right through Unit N on the normal distribution and then into the t-distribution in Unit E. So let's take a look, for instance, at what we've got here is we've got the norm.dist function. You can see this in C42, where we put in an x and a mu and a sigma, and we put in a true, and it will give you the area from some point down. Now, one thing I want you to note when you're reading this is that when we're looking at hypothesis tests, then the term lower tail tests will have some meaning behind it. Upper tail tests the same way. But for now, what I'd like you to think of it is whenever we're dealing with a less than problem, so we're looking at the probability that x or x bar or t is less than or equal to some amount. Upper tail tests is when we're looking at the probability that x or z or t is greater than or equal to some amount. So when we say lower tail tests and upper tail tests, that can be a little confusing at first because it really means from some point down or from some point up. So when you take a look, for instance, at the norm.dist function, which we used back in Unit N, that was used when we were looking at the probability that of x from some point down, even if x was in the upper tail. So if we had something like a mean of 60 and we wanted to find the probability that x is less than 90, the important thing is the less than 90. So it means from 90 down. So we would be using a norm.dist function. If we wanted 90 up, then we would do a 1 minus norm.dist, because the norm.dist always gives you from some point down, so 1 minus will give you from some point up. Now, what I want you to notice is when we take a look then at doing the same calculations in Unit E, instead of using an x, we use an x bar, and then we have a mu, and then instead of using a sigma, we have sigma over the root of n, the square root of n. So we have the same norm.dist functions, norm.dist from some point down, 1 minus norm.dist from some point up. It's just that we changed the arguments a little bit for that. It's the same kind of animal when you're dealing with z values. So here's the standardized norm distribution. Norm.s is the same as z, so a z distribution informally. So a norm.s.dist function will give you the point from some z value down. And all you do is put in your computed z value. I show that as a z star. from some point up, it would be 1 minus a norm.dist function. Maybe I should make these just a little bigger so you can see. I'm not worried about the two-tailed tests at this point, so don't be concerned about those. When we get into hypothesis tests, they'll make more sense. It's the same with the t-distribution. So when I'm looking at some point down, I'm using a t.dist function, and it will give me as an answer a probability, an area under the curve. Its arguments there are a computed t value, so a t star, degrees of freedom, and then true. Now, if I want to go from some point up, I can use a 1 minus t-dist function. But there's actually a built-in function called t-dist right tail. And so that will give you the area of some point t star up. It's exactly the same as 1 minus a t-dist function. So you can think of t-dist by itself as being a left tail test from some point down. And if you tack on a dot RT, it's from some point up. Why don't they do that with the normal distribution functions? I don't know. It's just kind of goofy. And again, don't worry at this point about the two-tailed tests. So I just want you to focus in on these guys right now. Now, let's take a look at these things called critical values. And this is something actually that we were introduced to back in Unit N when we were given this kind of problem. Remember, it was on page N12 where we were asked to find an x value that corresponds to, say, 10% in the upper tail. And so we were given a mu, we were given a sigma, we were given a probability. So you can see the three arguments there. And it returns as an answer an x value. We use the norm inverse function in Unit N. Again, you can think of this as being that these are less than and these are more than or greater than. So when we were looking at what's the probability or what's the x value that has, say, 90% from some point down, you'd be using a norm.inverse and putting in 0.9. If you're looking for some point up, it would be 1 minus that. So if I said, what's the probability, what's the x value that has 5% in the upper tail, what you would do is you would put in a norm.inverse and then 1 minus the 5%. So you would put in 95%. Now, I think the example I've got is actually 90%. And so that gives you the upper 10%, the lower 90%. And again, we're not going to, at this point, worry about the two-tailed test, but when we take a look at confidence intervals, we will. Same with the z values. So we have a norm.s inverse function. Will give you a z value that corresponds to some area down. Now, you'll notice that I've got a symbol in there which is alpha. And alpha is introduced in Unit E as the level of significance. And that will be really important when we get into hypothesis testing, but also we're introduced to that in confidence intervals. So we'll see that in this right-hand column, column E. I'm not going to look at that right now. I just want to focus in on these two columns at this point. So alpha is an area. It's 5% or 10% or 1%. And so if you put in norm.s.inverse and then 5%, it will give you the corresponding z value. In this case, minus 1.645 corresponds to 5% in the lower tail. If I want 5% in the upper tail, I could just take the negative of minus 1.645, or I could put in a norm.s.inverse and then 0.95. So 95% down is 5% up. It's the same with the t-distribution. So with the t-distribution, we use a t-inverse function, just like we used a norm-inverse function or a norm-s-inverse function. So with a t-inverse function, you put in your alpha or your probability, your area, and you need to also put in your degrees of freedom. And it will give you the area from some point, or it'll give you the t value corresponding to an area from some point down. So this is saying that minus 1.708 is the t value in a t distribution of 25 degrees of freedom that has 5% in the lower tail. 5% in the upper tail, which means 95% down, would be positive 1.708. All right, let's put that into practice here with some of the problems that we were working through in Unit E. So I'm going to go to another page over here, the calculations, and we're going to take a look then at calculating the Unit E probabilities with Excel. And again, I'm using this document, critical values and p-values using Excel, the page we just looked at. So let's take a look on E8, and I'm actually going to take you over to the manual here, and we're just going to take a look here at E8. And so we went through the central limit theorem, the first and central limit theorems, and then we talked about how to calculate probabilities. And we came to a problem here. I worked through one here, and then I actually left you one for homework. It was this one right here, which was 5A. Now, some of these problems I actually had to go in and finish them, but I'm going to afterwards erase them, and then we will take them up in class in our synchronous session here. So I think I left you with the blue part here, which was just the first couple of statements, and I finished off the problem here. So this is the problem. Suppose the distribution of monthly phone bills in Red Deer is normal with a mean of 280 and a standard deviation of 40. So that's our mu and our sigma. What's the probability that a sample of 36, that's your little n, will yield an average? So a sample average is an x bar of 270 or less. And so you can see that written right here. So I've got, oops, what happened there? So I've got here a funny looking line right here. The probability that x bar is less than or equal to 270. And I've drawn a picture below of what that will look like. So that is looking for an area from some point down. That means that if we're looking for an area or a probability, that is a DIST function, not an inverse function, but a DIST function. And if at some point down, it'll be a norm.dist function. So let's take a look at, first of all, what it looks like when we do it by hand. If we were to calculate the z value, we would get a minus 1.5. We would look that up in the table, and it would give us 0.4332, which we would subtract from 0.5, and it gives us an answer here of about 7%. So let's go back now over to here and show you how you would use the norm.dist function. So we've seen the norm.dist function before in Unit N, but in Unit E, what we're using here then is, this should actually say x bar right there. So it's an x bar value, and then a mu, and then sigma over the root of n, and then true. So here's the problem, the one that we're just looking at, the phone bill problem, and we're looking for the probability that x is less than or equal to 270. Remember, we don't get hung up on the sign, whether it's less than or equal to or less than. The important thing is that it's pointing to the left. It's less than, not greater than. So let's put the answer over here, and I'm just going to build the norm.dist function. I can go into formulas, more functions, statistical, and go down here and find the norm.dist functions. So here's norm.dist and norm.dist. So the norm.dist function, if I click on that, it will ask me for an x value. So I'm going to type in here 270. Remember, it's always more efficient to put those numbers into cells and reference those cells, but for this course and for marking purposes, it's a lot easier if you just type them in as constants. The mean is 280. Standard deviation is actually not just 40, it's 40 divided by the square root, the square root, so there's a function called square root of 36, which was our n value. So you can actually just type in like that. And then the quantitative is the word true. With a norm function, in fact, with the norm functions and the t functions, we're always going to be using true. It was only with the binom dist functions that we sometimes used true, sometimes used false, but we'll always be using true from this point on. So this is what we get for an answer. It's 0.07. And I'm going to actually just copy that, put it over here. I'm going to close this, and I'm going to put an apostrophe there so you can see the formula. So again, take a look at this formula here. It's a norm.dist. A dist function is used when you're looking for a probability as an answer. It's got as its arguments the x value, the mu, and then sigma over the root of n, 40 divided by the square root of 36, and then always true as the last argument. Okay, let's come down here to page E9, and I'm just going to move over to here, page E9, and this is talking about the finite population correction factor. And so we went through a problem here. It was this particular guy. I think that's the guy that we're doing. Yeah, that's the one that we did in class here. And it looks like quite a jumble because I had a number of things on here, but just let's take a look at what we had here. Suppose it's known that the 200 instructors, so that's big N at RDC, and there's actually a lot more than that, but I'm just using a simple number here, watched television an average of 15 hours per week with a standard deviation of 5. Those are all in the statement about a population, not the sample. So that's a mu and a sigma. What's the probability that a random sample, so as soon as you're talking sample now, you're into little n's and x bars, and later on we'll see s's. So a sample, a little n of 30, will yield an x bar of 16, at least 16, so 16 or more. So I've drawn a picture down here. You can see down there where I've got 15 in the middle, and I'm looking for 16 up, and that's on the distribution of x bars on sample means. So we went through a process here where we standardized this thing. We had to use this FPC factor, finite population correction factor, and that gave us a z value here, and then we looked that up on the table, and that came to 0.3830. Subtract that from 0.5, and that gave us 12% as an answer. So that's how we did that by hand, and you can go back and take a look at the video where we talked about that. But I want to talk about that with how we do that with Excel. Now, one thing to note about Excel is I could do this right in a norm.dist function. The problem is that it starts to get a little messy is if you take a look at this last part here, which is the standard deviation divided by the square root of n, and then you'd have to tack on the FPC factor, the square root of n minus big N minus little n over big N minus 1. And so what I did is to do this in 2 steps. And the first thing that I did then was I calculated then the z value, or the z star value is what we'll call this, a calculated value from this point on. So here's our original problem. X normally distributed, mean of 15, standard deviation of 5. capital N is equal to 200, little n is equal to 30. What's the probability of getting an X bar? That's what that should say there. Actually, it should be an X bar up here. The problem is that it's hard to get that particular symbol in Excel, especially when you're using a Mac. You can use something called a diacritic, and that's where you type it in X and then you press a button. It actually backs up and it combines it with an overbar, but it's hard to do that on the Mac. So anyways, it's an X bar greater than or equal to 16. And so what I did was, this is just the formula here, X bar minus mu over sigma divided by the square root of n times your FPC factor, right? So that's this guy over here in red, right in here. And so I did that, and this comes to 1.19, and that's what we get over here, 1.185. I guess it rounds to 1.19. I like to keep things to about 3 decimal places until the final answer. So here's how you do that in Excel. But the important thing here is that we're going to be now using a norm.dist function in order to calculate the probability. Now, remember, a dist function is when you're looking for a probability as an answer. And this is a normal distribution, and so we're using a norm.s because it's a z. And then in this case, we're looking at going up, so what we'll do is a 1 minus that norm.s.dist function. So let's type that in, and that will be equals a 1 minus, and instead of going to the formula builder, I'm just going to type it in here. So norm.s.dist, and when I push my bracket, you can see it asks me for my z value. So the z value is the 1.185, which we calculated, and then you still need to put in a true, and it should give us an answer here of 12%, which was what we got when we did this by hand. So I'm going to just go here and go like that. All right, so that's the first part of Unit E. It was using the normal distribution function, so we're using Z, but we were talking about X bars, and then we added the finite population correction factor, so I did that in 2 steps. Now we're going to jump over to the T distribution. So in the T distribution, that was introduced on page, well actually in page 10, and then we talk about this in the next few pages. And we came to this particular page here where I walked you through the table. So I'm going to take the first couple of these, the first 2 cases. Case 1, what is the probability that a T distribution with 24 degrees of freedom is greater than 2.5? And then the one below is looking at the probability of T with 20 degrees of freedom less than -2. So in one we're going up, and another one we're going down. Let's take a look at that over here. Now, first of all, I want you to note that these are dist functions because, again, we're given the particular T value, and what we're looking for as an answer is the probability, the area. So that makes it a dist function, not an inverse function, which we'll get to in confidence intervals. And I've got 2 of them here just written. Those are the same 2 that you saw back on this particular page back here. Let me just take you back there. Remember, so I'm talking about these 2 guys right here. And so let's go over here to the calculations here. So I've just written those out here. Sorry, I was in the inverse section there. I should be down here. There we go. So it's these 2 guys that I'm talking about there, the T.dist and the T.dist.right tail. Okay, and so let's take a look then at over here, the calculations. There we go. So the first one was, what's the probability of having a t with 24 degrees of freedom greater than 2.5? In this particular case, remember, we're looking for a probability, so it's going to be a t dot dist. And because we're going up, it'll be a right tail dot rt. All it asks you for is the x value, or it's actually the t value, so it's 2.5, and then the degrees of freedom, which are 24. Those are given to you in that problem. And that is an answer here of 0.0098. I took it to 4 decimal places because if you go back to this page here, the part in green right here, it says the answer is somewhere between 0.005 and 0.010. So it was between the in between the 0.5% column and the 1% column. So this gives us something a little more accurate. It's 0.0098. And so I will copy that and then just put a little apostrophe in front of that so you can see the actual formula. Okay, so that's when you're going from some point up. Now when you're going from some point down, and by the way, it doesn't have to be a negative number that you're going from some point down. It could be from 2.5 down. But in this particular case, we're looking at a t with 20 degrees of freedom from -2 down. We're looking for a probability, so it's a t-dist function. And that's actually where you end. It's not a t-dist right tail, it's just a t-dist, and that'll give you the area from some point down. So put in your bracket, put in your -2, so -2, comma, and then your degrees of freedom is 20, and the answer here is, oh, it says I'm missing something. I'm missing, comma, true. So, and that's kind of goofy again. The t-dist right tail doesn't ask for the true or false cumulative. The t-dist does. I'm not sure exactly why they do it that way, but whatever. And there's the answer, is 3%. I'm just going to copy that over, and I'm going to put an apostrophe in front of that, like that. So that's what we've got there. Now, incidentally, that you could also do, oh, sorry, let's go back up here, the t-dist right tail. You could also do that as a 1 minus t dot dist, which is the area from some point down, 2.5, and then 24 degrees of freedom, and then you have to put in true. And what didn't I like about that? I had a period instead of a comma. There we go. So you get the same right there. So just to show you then that the t-dist always gives you the probability from some point down. So if you wanted to go up, you could do a 1 minus, but there is the built-in RT function that does that for you. All right, that is that. The next thing that we did is on page E14, number 8. So let's take a look at that one there. This is not just looking at the t-table, it was actually applying it to a problem. So it might be good to just take a quick look at that one. So that was E14, number 8. And it was this one we went through in class. It's hypothesized that business students, this is actually getting us into hypothesis testing. And so the t-dist function then gives you an answer which we'll call later a p-value. And we'll formulate all that later. So it's hypothesized that the business students have an average IQ of 100. So that is a hypothesized mu. And we're going to take a sample of little n is equal to 50, and we're going to get an x bar of 110 and an s, that's a sample standard deviation, of 20. And so what we did in this particular case is we noted that because we don't know what S is, we don't know what sigma is, we have to use S, and so that makes it a t distribution. We're looking for the probability of getting an x bar greater than or equal to 110, and that is shown in the picture down here, right there. And so we used a t formula to get a t value of 3.54, and then we looked that up in the table, and it turned out to be something less than 0.005, so really small, something less than 0.5%. Okay, let's take a look at how we do that over here. So what I've done here is I took all of the stuff which is given to us and I calculated the t star value. So x bar minus mu over s divided by the square root of n is right here. So there's the actual formula that I used to do that. And so that gives me 3.54 or 3.536 to 3 decimal places. And now what I'm going to do is I'm going to be using the DIST function. And because I'm looking for a probability as an answer, what's the area? But I'm going from some point up, so that means it's going to be a t-dist right tail. So equals t.dist.right tail 3.54, comma, degrees of freedom will be n minus 1, so 50 minus 1 is 49. And that gives me that as an answer. Remember I said that it's something less than 0.005. It's actually 0.0004. So there you go. Now, last thing we're going to do is we're going to take a look at confidence intervals, and now we're going to move from DIST functions to inverse functions. So let's take a look at this here. And we're going to be using the t dot inverse. So an inverse function is used when you're given a particular probability, and when we're talking confidence intervals, it's the alpha, or alpha over 2. And when you stick that in as one of the arguments, it gives you what we call the critical t value or the critical z value. That's the t alpha over 2 or z alpha over 2 values which are used in the formula. Let's take a look on page E23. And I'm just going to scroll there and then I'll take you to it. Let me just find it first. Okay, let's go over here. So here's E23 here, and we're taking a look at number 13. So it's actually this guy down here. Now, in the video, I left this for homework, and so I'm going to afterwards erase this, and then we'll take it up in class in the synchronous session, but let me walk you through this. The mean monthly expenditure on gasoline per household in Middleton is determined by taking a random sample. So we're talking sample, so that 36 is a little n, and then we get a sample mean, that's an x bar of 200, and a sample standard deviation, which is an S of 60. And then we're looking for a 90% confidence interval for the mean. So what we have here, this is actually really exciting from a stats point of view, because we know nothing about the population, and we don't need to because the central limit theorem kicks in. We'll go through that flow chart. I'm not going to do that right now because I'm focusing in on the Excel functions, but go through that flow chart and you will see that you'll end up using formula number 3 here. Before we get there though, we're looking for a 90% confidence interval for mu, and so 90% confidence means we have a 10% level of significance, and that is the amount of allowable error. Why do we allow any error? Because we can't sample everybody. Okay, and so we can't be 100% sure unless we sample everybody, that is, take a census. As soon as you take a sample, then you introduce uncertainty, and so we're going to come up with a 90% confidence interval, meaning that we have to be okay with 10% possibility of making a sampling error. That gives us an alpha of 10%, and in a confidence interval, you split that alpha in half, and so that alpha in half is going to be 0.05. When you go through the flowchart, you will get this here. And again, this is going to make more sense when we go through it in class. But it's a t distribution because we don't know what the sigma is. And so it's going to be an x bar plus or minus a t alpha over 2 n minus 1. And that's a little hard to see there. I'll just write this outside like that because I had a circle around it. Those are just subscripts to tell us the column and the row to look at it in a t-table, or when we get to a t-inverse function, the first two arguments of it. So what this is in terms of a t-distribution with n minus 1 degrees of freedom, so in this case would be 35 degrees of freedom. Yeah, n was equal to 36. So what we're saying is we want to find these values here that have 5% in each tail. And that leaves you with 90% in the middle. If you look it up in a table, it'll come to minus 1.684. That's the closest one that we have. I think you have to go to the 30 degrees of freedom because it goes from 30 to 40. So no, that's the 41, right? So then what we do is we plug that in and we get our confidence interval that looks like this. What I want to show you in Excel is how do you get this 1.684, which you can then plug in by hand to get the confidence interval. So that's what we're looking for, is the 1.684, that critical t value, the t alpha over 2 value. Okay, let's go over here. An inverse function, and I'm going to go back here and say that we use inverse functions when we're looking for areas. Again, remember over here, we were first introduced to that in Unit N, where we were given a probability and we wanted to find the x that corresponded to that probability. And so we used a norm inverse function. The last column here in this table is for confidence intervals. So these are the critical values for confidence intervals. And let me just make this a little smaller so we can see the whole page here. Just a little bit more. There we go. So for a normal distribution, these would be the critical values. Now, they're not actually used when you're just dealing with a regular normal distribution, but when you are looking for a critical z value, a z alpha over 2, this is what you use. When you're looking for a critical t value, we use a t inverse dot two-tailed test. And then what you do is you put in the whole alpha, not alpha over 2, and your degrees of freedom. So it's a little goofy. We could use either one of these ones here to get the upper and lower bounds, but this also will do it for you. And so let's take a look at how that works here. So this is the problem that we had. This is the one I just read out for you. 90% confidence interval for mu. Alpha is 10%, so alpha over 2 is 0.05. Let's get the critical values here. So what we would use here then is a t dot inverse, right? Because we're given the area and we're looking for the critical t value. And then because it's a confidence interval, it's a dot two-tailed, like that, comma. Probability is, and here's the thing you need to remember about the T inverse dot two-tailed is you don't split the alpha in half. So you would just simply put in 10%. And then you put in your degrees of freedom, which in this case is n minus 1. And so that's going to be 35. And there's our 1.69. That was the same thing that we had back over here, 1.684. Remember this one here, I said that we had to interpolate, or we had to, go to 40 degrees of freedom because there wasn't a 35. So it's pretty close, but this is the actual number right here. Okay, so that's what we would use here. I want to just show you that here. By the way, you wouldn't need to do this, but if you used a T dot inverse function, then you would put in half of alpha, so alpha over 2, and then 35 degrees of freedom, and that'll give you the lower bound value, minus 1.690. Okay, and I rounded the one below here to 3 decimal places. Okay, or if you wanted the upper tail value, you could do a T inverse, and you'd actually have to put in 0.95. There is no RT function. So again, it's kind of goofy that it has it for a DIST function, but not for an inverse function. So there you get the positive value here. So I'm just going to show you all of those guys there. Okay, so T inverse 0.95, 95% below, 5% above gives you the upper value. And I'll just take that to 3 decimal places. Okay, the lower value would be just a T inverse with 5%, but because you're dealing with confidence intervals, there's a built-in T inverse dot two-tailed. You just put in the 10% here, and without splitting it, and your 35 degrees of freedom, and it gives you that value. Then what you do is you stick it into your formula. So you grab your x bar, which is 200, minus 1.690 times 60, which was our standard deviation over the square root of 36, and that gives you your lower bound, and then the upper bound is 200 plus that. So that gives you then your confidence interval from mu, which is right here, which is what we got. We got pretty close to that by hand because remember we were using 1.684. Okay, last problem I want to show you is doing a confidence interval for a proportion. And so again, I'm going to show you this in class when we get there, but this is actually, what page is that? It's number 15. It's page E26. There we go. Number 15. And so let me just take you there, right there. So E26 number 15 is this guy here. A rancher is interested in estimating. Whenever you see the word estimating, we know that we're talking confidence intervals. The percentage, so it's going to be a confidence interval for P, the binomial P, of his 500 cattle, that's a big N, that have a certain parasitic infection. So he takes a sample of 36, which is little n, and finds that 9 of them are effective. So 9 out of 36 is 0.25. That's your P bar. And we're looking for a 90% confidence interval for P. So I've got that all written over here. So I've got a big N. Let me just change colors here. Here's your big N of 500, little n of 36. 9 over 36 is 0.25. 90% confidence interval means your alpha is 10%, and alpha over 2 would be 5%. You need to do the check, right? Is n times p at least 5? Is n times 1 minus p at least 5? Check, check, it is. Go through the formula sheet, and you'll find that you'll be using formula number 6 that looks like this. P bar plus or minus a z value, z alpha over 2, and then square root of p bar times 1 minus p bar over n, and then you've got your FPC factor because you've got your big N there. So again, we're going to go through this in class. But what I want to do is show you how do you get that 1.645 using Excel. So that's what we're going to do, and the rest we would do by hand or using Excel formulas, okay? But the function that we're looking for is a norm inverse function. So we're actually going to be using, do we have an example of a norm inverse? I guess not. Okay. So this is going to be a norm dot s dot inverse, and all it has as an argument here is just your alpha. That's all it is. Okay. And let me just clean that up a little bit so you can see that better. Actually, I have to change this to a symbol. There we go. Okay, so that's what the thing looks like. I might as well put it in red because the others are. Okay, so this really is a binomial problem, right? N is equal to 36. We don't know what P is. We know what big N is, 500. P bar, 9 over 36, which is 0.25. We're looking for a 90% confidence interval. We do our check, and that works out. And we're looking now for the critical value for the confidence interval, a plus and minus value. This is a Z value, so it'll be a norm.s dot inverse, right? Inverse functions are when you're given the alpha, in this case, alpha over 2, and we would use a norm.s because it's Z. Now, in the t distribution above, the t dot inverse dot two-tailed, you didn't split the alpha, but here you do. So you have to put in alpha over 2, and that will give you the 1.645. Okay, so I'm just going to go up here and edit this and say this is actually divided by 2. So there is your lower bound. Now, you could, of course, if you wanted the upper bound, you could put in 0.95, and that means 95% down, 5% up, and that gives you positive 1.645. I don't think that that's really necessary because, of course, it's going to be plus or minus anyway, so you could just simply use the negative one and just put in the 5%, which is alpha over 2. From there, we would plug that into our formula, and so there. So it would be P bar 0.25 minus 1.645 times the square root of P bar times 1 minus P bar over N, and then times your FPC factor, square root of big N minus little n over big N minus 1. So that gives you your lower bound of 14%, and then 0.25 plus that mess gives you your upper bound. So here's your confidence interval here, which is that P is between 14% and 36%, and we're 90% sure of that. Whew. So that takes us to the end of this particular lesson on Excel. These are all the different DIST and inverse functions that you would need in Unit E, and you'll find that these will be the same ones that we will use in Unit H on hypothesis testing. And so we will end it here. Thanks for watching.